The next speaker, and I hope I get your name right, Qinan Wang. Yep. John Hopkins and data science, LSSDC data science fellow. And he will talk about supernova lightcurves with Kepler.
And what a perfect segue that last question was to Qinan stock and constraining different kinds of type 1A progenitor scenarios.
Thank you. Yeah, I'm glad that people are also interested in type 1A progenitors, and that's part of my talk today. So hi everyone, I'm Qinan Wang, and I'm coming from JHU. I'm a graduate student working with Army Rest, and I'm also associated with the Transient Science as STSCI group. And so today I'm going to talk about our research with about using Kepler and TESS high-cadence lightcurve to constrain the supernova explosions. And the background plot I show here is the original drawing from Johannes Kepler, like 400 years ago, on his discovery of his famous supernova. And I find it very interesting that after a few hundred years, we are using a telescope named after him to study the supernova physics. And although this telescope is not originally designed for time domain, so as many of you may know, so Kepler telescope is originally designed to discover exoplanet. And so in order to resolve this eclipsing light curves of exoplanet passing through these holes, it's designed to take exposure for every 30 minutes, and it's also designed for a very large field of view. And these features, so later on, our time domain astronomers find that these features can be well utilized in time domain astronomy to resolve the most fast evolving features that is hard to catch from the ground. And here I show two examples. And the left plot here shows a real type of CV, and the right plot here shows a mysterious fast evolving transients. And you can see how fast they evolve. Like their magnitude rise for about 5 to 6 meg within 2 or 3 days. And such features is very hard and also can be very expensive for ground-based observatory to catch. But for Kepler, it's easily observed, and with this light curve, we can do some very nice model fittings to see what their nature is. And so, but unluckily, Kepler stopped functioning in 2018 due to the lack of fuel. But later on, luckily in the same year, we have its successor up in the sky around the same time, which is called TESS. So the TESS is designed to find the exoplanet around the brown dwarf, and it has a similar capability of as Kepler, with a much larger field of view at a cost of a much larger pixel size. And this do cause some difficulties in data reduction. And the lower plot here shows the survey strategy for TESS. So it will continuously observe a sector of sky for 27 minutes. And to solve the issues in data reduction, our group has developed a pipeline called the TESS Reduce. And this pipeline has been up in GitHub. So if you are interested in any of the transients that may be covered by TESS, you can just download it and run a quick one-line reduction to see how it looks like. And so then I'm going to talk about the physics I'm interested in and want to do with Kepler and TESS. So I'll first start with type 1A thermonuclear supernova, and later on I'll talk about a few cases we studied with the core collapse supernovae. So I think you may learn a lot about in the previous talks about type 1A. So you may know that it has a very important role in cosmology, and it's most likely to be an explosion of carbon-oxygen white dwarf when they approaches Chandrasekhar mass. And and you may also heard about there are a lot of debates on what is progenitor is. To be specific, we believe that type 1A supernova explosion happens in a binary system, and there are debates about what its progenitor star is and what is the trigger of the explosion. And so here I'm trying to give you an overview of the existing progenitor models. So based on what the companion star in the system is, you can divide them as single degenerate model in which the companion star is a non-degenerate star, which is a main sequence star or a supergiant, or it can be a double degenerate system where the system consists of two white dwarfs, and they may when they spiral with each other, they may tidally destruct each other, or there might be some head-on collision, which is more violent merger. And one feature that may help in distinguishing these two models, not only two, there are a lot of models in the observation, is to search for the bumps at the very early time, roughly within the first 5 days after the explosion. And the idea was first proposed by Dankinson in 2010 that in single degenerate case, the supernova ejector will collide with the companion and then create a very bright bumps at the early time. And the right plot here shows how it happened. And the orange denotes the ejector, and while the blue points here denotes the companion. And you can see the bow shock formed by the collision outlined by the black line here. And you can see the below panel shows the light curve in different band, and you can see this bumps happens only in the first few days. And later on, people also propose that in other models, there might be some similar bumps with slightly different shape and colors, and it's mainly related to the ejector structure. So you can imagine if there are some nickel 56 distribute as a shallower layer of the ejector, when it decays, it will create another bump at the early time. And such a distribution, one mechanism is that in double detonation model, the first detonation at the surface may create some nickel 56, and that may lead to a slightly different bump. And so what we need, in fact, to differentiate in between different models is that we really want some high cadence and early light curves at early time. And if we can take multi-band like measurements, that will be even better. And such study has been done from the ground. Here is the most famous example, the Supernova 17 CBV. So LCO did a very extensive follow-up from the ground, and you can see there is a very clear bump early on, and this bump is very blue and extremely bright in the U band. And you can see it lasts for only like 4 or 5 days. And LCO really did a great work that they take like a few hour cadence like curves. And however, this kind of observation is kind of hard to do, and it's kind of expensive for ground-based survey. And then but on the other hand, the Kepler will naturally observe some type 1A from the beginning with very high cadence. And the famous example is then the 2018 OH observed by the Keck group. And here is a Kepler-like curve. And you can see in the zoom-in plot that at the early time, the supernova flux does not follow a smooth power law rise. And if you subtract from the beginning, you will see a clear bump with an amplitude of 3% of the peak flux. And it's kind of impressive discovery. And later on, people did some model fitting to that with the 3 models, the double detonation model and shallow nickel 56 distribution model, and then the companion interaction model. And overall, the residuals are within 0.1 magnitude, and given our uncertainties in underlying supernova physics, I would say that all 3 models seems to be a good fit, and while the double detonation model seems to be relatively better. And then we looked into the early color evolution, and luckily we have the slope measurements at the very early time in I band. And when we compare with K2 band, and we study the K2 minus I colors and compare that with the different models. And this color seems to be really blue and seem to match the collision model or the surface nickel model better, and seem to disfavor the double detonation model. I think someone mentioned that earlier this week that for single degenerate model, you will expect to see some hydrogen and helium in later stage spectra, because some of them might be expelled by the shock from the companion star. And people did such search, but the result is that there is no such features. And this again seems to be a evidence that disfavoring the companion interaction model. So combining all this extensive follow-up and the evidence, it seems that we are still hard to get to reach a conclusion on the 18OH about what each progenitor is, and especially consider that we have a lot of uncertainties in the underlying supernova flux and the colors, and we seem to need to know more about the type 1a at the early time. And then one natural choice is to see if we have any other objects, nice objects covered by K2. And so here is all the type 1As are covered in K2 mission. And you can see besides the brightest 18OH, the others seems to have a smooth power law rise. But one question comes is it because the noise too high that the bump was not seen? So I look into the case of 2018 OEGK, which is the second brightest ones. And if you zoom in and do a power law fit, and you can clearly see that given the uncertainty, given the noise level, given the noise level, the 18 AGK seem to follow a perfect power law rise and without any hint of any bumps. And another good thing about 18 AGK is that we have some very early on color measurements from the decam. And here I show you the plot of the decam color in G minus I band in comparison with other plots. So the red is the AGK, and the black points are the 17 CBV, and the others are the supernova without bumps. And you can see clearly a trend that all of these supernova in G minus I band seem to evolve very slowly within the first 10 days. And there seems to be a very clear gap in between the 17 CBV and the other type 1As. And this becomes a direct contrast with other survey on the other research on the early color of type 1A. So here I just show two examples in B minus V band and ZTF results in G minus R band. So in the plot here, so in previous study, people conclude that there might the super type 1A may divided into blue, the so-called blue and red group in the B minus V band, in which the red group has a much redder color and has a very fast evolving trend, and while the blue seems to have a very constant color and bluer initial color. And later on, the ZTF sample from the ZTF's research, they conclude that the blue and the red sample seems to have smaller difference in G minus R band. And of course, I have to emphasize to you that all this research are kind of like done with very limited sample, and of course they can be biased. But I think one thing is very clear that type 1A seem to behave very differently in different bands at the early phase, and so people may need to pay extra attention because when they're trying to search for the early bumps in different bands. And so later on, I also did another analysis trying to put constraint on the single degenerate model to see in which part of the parameter space we can rule out the existence of a non-degenerate companion. And
5 minutes.
5 minutes. Sorry. How to proceed to this? Oh, yeah. Oh, yeah. Oh, so okay, so what I did is to basically add a bump created by certain non-degenerate companion on top of 18 AGK light curve and run a bump detection algorithm to see if they can be detected. And the red region basically shows the results that the bump is still not detectable. And you can see, even with the 18 HK light curve, it's still hard to exclude some of the existence of some companion. And that requires that we need to do some statistical study to fully exclude some progenitor scenario. And that's kind of thing I'm doing. So I'm currently working on a large statistical sample of around 100 type 1A in Kepler and TESS. Okay, so next I'm going to talk about the scenario for core collapse supernovae. So as many of you may know that so basically this video shows the so-called the shock breakout light curves. So when the supernova shock reaches the surface of the progenitor star, it will suddenly broke out and create a very bright flash, which is very bright in UV and X-ray, which lasting for less than a few hours. And such signal is hard to catch even from TESS and Kepler. But on the other hand, we can, but following that, within the first few days, the material heated by the shock will gradually cool down and create a light curve, so-called shock cooling light curve, which will last for a few days and bright in optical and near infrared band, and is perfect indicator for constraining the progenitor properties, and is detectable by Kepler and TESS. So while so Patrick Armstrong did a little research on the supernova 17 JGH. So it's a typical type 2b observed in K2. And you can see the shock cooling light curve here within the first 10 days after the explosion. It's pretty bright and even brighter than the radioactive peak. And Patrick did we did a model fitting to that, and out of a few models, we found that the progenitor is most likely to be a yellow supergiant with the envelope radius to be 130 solar radius and the envelope to mass to be 0.6 solar mass. And in this research, Patrick also demonstrates that the rise part of the shock cooling light curve will be a critical part for constraining the progenitor. And without that, the fitting result will be obviously very overfitted and very biased. So in order to constrain the core collapse supernova progenitor, this part will be very necessary. And we discovered another type 2b supernova in TESS, which is 2021 ZBY. And this time, luckily, we have Atlas O-band measurements within the first 5 days around the rising phase. And thus the model fitting performs a bit even better than the case of 17 JGH. And so due to time limit, I just want to show you the result. The result shows that the yellow supergiant and blue supergiant have similar performance, and both of them has very low residuals, and they seem to have the progenitor of 21 ZBY seem to be a bit larger than 17 JGH, and kind of around the range that previous study with the shock cooling curve have given us. Okay, so just want to come to the conclusion summary part. So I've shown you that the Kepler and TESS has the ability to catch the most rapid feature of the transients, and including the early on bounds. And with these features, we are able to constrain the progenitor of type 1A and the core collapse supernova to a very high precision. And yeah, I think that's the end of my talk.
Perfect timing. Thank you very much.
Thank you.
Questions? I have it. Oh.
Really nice talk. So for the 21 ZBY data,
Yep.
My first question is, you have more complete spectra?
Yep.
Because I remember 17, the other one, JGH, just like didn't have a lot of spectra, so there wasn't a lot that you could really figure out.
I think in Patrick's paper, there is only one spectrum
Yeah.
around the peak, around the radioactive peak.
Okay, that's very
For
cool.
21 ZBY, we have a spectral around the shock cooling peak.
Okay, awesome. And my second question is just for the shock cooling models, do you think that you're going to try to differentiate between the blue and the red supergiant? I mean, all those models are the Sapir and Waxman, and then it's the different like N values. But it's like they give very different masses. Those are really very different
Yeah.
envelope mass constraints that would indicate very, very different progenitors. But they both really fit your model, your data really well. Do you have like ideas about how you're gonna?
Yeah, so
discuss that?
so the chi-square, so the number of parameters in the models are the same, and the reduced chi-square is almost very close. So there is only like two, like the difference is roughly 2 in between these two model fittings. So I would say their performance is pretty similar, and it may be hard, even with that amount of data, might be really hard to differentiate these two models. So yeah.
Alex, oh,
Yeah, great talk. My question is, the TESS and Kepler survey has data which is super highly cadenced, right? But
Yeah.
when you think about coming into the LSST era, like, do you know what bands we should be most sensitive to, like if we want to model or characterize cooling envelope, or even the earliest bumps of 1As, and like what would be the sufficient? I mean, it's a hard problem to solve. So what would be a sufficient number of detections, or is there a time frame where we can just put our place, and this would be the most sensitive place where we can get more signs out of it? You mentioned about the peak rise time for cooling envelope. But do you know what filters are more sensitive to it?
Yeah,
Like
so,
UV? Go ahead.
Yeah, that depends on the model. So if you look at the Dan-Cassens model, so you can see that the blue band is the brightest one. But in some other models, like the double attenuation model, the bump seems to be a bit redder. So it all depends on the model. So I would say multi-band observation will be very crucial to resolve that. So it might be even plays the similarly important role as high cadence lightcurve. And you can see here about the cadence. So what you can see here is that the black point here, maybe I should do this. Yeah, the black point here is in fact the 6-hour cadence. And you can see in the case of 18OH, it's good enough to constrain the progenitor. And I would say it might be very beneficial if we can build a global network so that we can take exposure for a few hours, and that will be good enough to constrain the type 1A progenitor.
I want to point out that there is a global network by that name, the Las Cumbres Global Telescope Network.
This is Alex Kim from Lawrence Berkeley Laboratory. Micro lensing can affect the magnitudes and colors of supernovae when they're very, very small. So I'm just curious whether or not you thought about the prospects of detecting that.
Yeah, in fact, it's just around this workshop did I realize the important role of micro lensing. So far, I do not have a very good answer. So, but of course, that may be a very good thing to look at if we do have a detection of multi-peak, like supernova.
And while the next speaker, Lindsay, comes up, I'm going to ask the last question. I should really know this, but like, how extended is the TESS extended mission? Is there any chance that Rubin operation starts while TESS is still taking images and we can get very densely sampled lightcurves and colors from Rubin? How long is TESS going to be alive for?
I think it's already in the extended mission, so depends on luck.
Fair answer.